This is section 2. In the last section, we talk about the misconceptions in the most popular explanation, and I derived Bernoulli's equations to you. This section will start with Bernoulli's equation. Just as a quick recap here, Bernoulli's equation tells you that the pressure drops along streamline, the velocity increases, and vice versa. Now we'll look at a curved streamline. If there is a curved streamline, if you have learned high school physics, you will know there's a centripetal force acting on the particle. This centripetal force is always towards the center of the curvature, and it's equal to mv squared over r. So what we will find is the pressure at the upper surface is greater than that at the lower surface, since there should always be a force pointing at the center of the curvature. So what you'll find is you can use the similar technique just as we have done in deriving the Bernoulli's equation. We can use the same technique. Mass is equal to rho AH. And here similar dP is equal to h, which is the height of the particle, times dP over dN. And dP over dN is similarly the pressure gradient. And n is the coordinate in the direction perpendicular to the streamline away from the curvature. So n is in this direction, and you get dP. Similarly, you can use two ways of expressing force. The first one is pressure difference times cross-sectional area, and the second one is using Newton's second law here. And finally, you'll get the pressure gradient is equal to rho times v squared over r. So you have got the equation for pressure gradient across streamlines, and as you can see, for straight lines, as r tends to infinity, the pressure gradient here is equal to 0. So we can conclude that if a streamline is curved, there must be a pressure gradient across the streamline, with the pressure increasing in the direction away from the center of curvature. So you can see here is a curved streamline, and there's always a pressure gradient in the direction away from the center of curvature. So the pressure gradient is always pointing away from the center of curvature. This is a very important rule, and you should keep it in mind. There's some very nice examples of curved streamlines in real life. It's a tornado, or you can call it is a type of vortex. And you can see here in the two-dimensional surface, it's circles of streamlines. However, if it's in three-dimensional space, it's spirals. But here we're just putting on the two-dimensional graph of a tornado. You can see it's curved streamlines. So using the rule, the pressure gradient is always increasing away from the center of curvature. So it's always increasing away from the center of curvature. So the pressure in the middle is quite low. And you can apply Bernoulli's equation to the streamlines near the center of the curvature. And Bernoulli's equation tells you that so let's say here the point here has pressure P1, point near to the center has P2. So you can easily tell that P1 is equal to P2, and applying Bernoulli's equation, you can simply deduce that V1 is smaller than V2. So the speed of air in the middle is quite high. So now we can explain the lift on wings, and we will do that in the next section.